In this video I'm going to introduce arguably the most important concept you'll learn all semester. It's the concept of a mole. Now, before I do that though, I do just want to define two terms first. So, one of them is the molecular mass, and the other is the formula mass. And we've talked about these a bit already, but I just want to make sure that I clearly define these terms so you know what I'm talking about. So the molecular mass is used for covalent compounds, and the formula mass is used for ionic compounds. And so molecular mass, again, you're just adding up the atomic masses for all of the atoms in a molecule to figure out what the entire mass from the periodic table is of that entire molecule. So for water, for instance, water is a covalent compound, so it has a molecular mass. There are two hydrogen atoms, each with an atomic mass of 1, and there's one oxygen atom with an atomic mass of 16. You add that up, and you get 18, with the unit being AMUs. And that is your molecular mass for water. And you can do the same thing for an ionic compound, again NaCl for instance. But if you recall, ionic compounds often form large crystal lattices. It's not just a single sodium and a single chlorine often, right? So instead of referring to molecular mass, since it isn't just a molecule, we refer to it as formula mass. But the math is the exact same. There's one sodium with an atomic mass of 23. There's one chlorine with an atomic mass of 35.5. 23, 35.5. You add those up, and you get 58.5 AMUs. So if you hear molecular mass or formula mass, that's what these are referring to, right? So I'll touch back on these in a second, but now I want to talk about what a mole is. So if I were to ask you what a dozen is, I'm sure you would tell me that it's 12 of something, right? Whatever we happen to be referring to, whatever kind of objects we're talking about, a dozen is 12 of those. Well, similarly, 1 mole equals 6.022 times 10 to the 23rd particles of whatever we're talking about at the time. It could be atoms, molecules, ions, electrons, whatever you want. And it might seem like that's kind of an odd, arbitrary number, but it's actually very important. Now, you don't need to know how that number came to be, but just know that it's a very important number, and it's actually known as Avogadro's number. So Avogadro's number is 6.022 times 10 to the 23rd. Right? So moles. The reason moles are so important is because they are the only unit that can be used to convert between different chemicals in chemical reactions when doing calculations. So many different types of calculations, whether relating number of atoms to molecules, or atoms to other atoms, certain molecules to other molecules. All of these calculations, the only unit you can be in when directly comparing the two different chemical species is moles. So moles ends up being kind of the hub of the vast majority of your calculations. Right? So, for instance, one very common conversion that you see is that moles and grams. So you cannot measure out the moles of how many moles of something you have in a laboratory setting. What you can do is weigh it out, so you can get the mass in grams. Right? So we need to know a nice way to convert between mass and grams, so we can take the species that we can measure and convert it to the species that we need for calculations. And we use that with something called, or for that we use something called the molar mass. The molar mass is basically just what we did here with the molecular mass and the formula mass. Now, remember, these are talking about, this is one individual molecule of water. This is one individual formula unit of NaCl. But if we have 1 mole of water, how much mass does it have? Well, the atomic masses on the periodic table also represent the mass per mole. So we can actually just take this exact same calculation, do it the exact same way, but instead of using the unit of AMUs, we can use the unit of grams per mole. So water has a molar mass of 18 grams per mole, and sodium chloride has a molar mass of 58.5 grams per mole. And this is actually the more common version of the units that you'll be using as compared to AMUs. So what does this mean? Well, let me rewrite it here. So we've got so water has 18 grams per mole, but you can rewrite that as saying 18 grams over 1 mole. Again, so that's the molar mass of water. Now, what that means is that if you have 1 mole of water molecules, so if you have 6.022 times 10 to the 23rd water molecules, because that is 1 mole, it would weigh 18 grams. That's what those units mean. So, let's say, for instance, if I weigh out a sample of water and it weighs 36 grams. And I want to know how many moles I have. Well, remember, we can put this over 1. Now let's use, since, if you recall back to dimensional analysis, I said anytime you have a unit that's a fractional unit, like grams per mole is, it can be a conversion factor between those two individual units. So, that's how we are going to very often use molar mass in this semester. So we need to cancel out the unit of grams. So let's put this grams in the denominator here, moles up here. So the 1 and remember, it's always 1 mole, so the number that you get from adding up the periodic table always has to stick with grams wherever you put the unit of grams. So 18 goes down there. Units of grams cancels out. So now we're left with just moles as our unit, and that's what we want. So let's multiply the numerators across. We get 36 times 1. Let's multiply the denominators. 1 times 18 equals 36 divided by 18. You do that, you get 2 moles. So that's 2 moles of water. That's 36 grams, right? So molar mass is going to be a conversion factor, and you can go from moles to grams or grams to moles, right? So, as I mentioned a little bit earlier, moles is often going to be used because it's kind of like the center of all, or at least the vast majority of calculations that you will be doing in the semester. So let's kind of draw that out. We've got moles of a substance. Let's look at some of the conversions that we can do from there. So as I just said, we can go to and from the mass of the substance. You know what we can also do, though, is we can go to and from the number of particles of that substance. And how can we do that? Well, we use Avogadro's number. Because remember, conversion factors can be written out as fractional units. They can also be written out as equations like this. So we say 1 mole is that many particles of whatever kind of substance we're talking about. So that is in itself a conversion factor. So let's say, for instance, so if we happen to have 6.022 times 10 to the 23rd atoms of something, and I want to know how many moles that is, right? Well, again, I can put this over 1. I can say 1 mole here, and I can say 6.022 times 10 to the 23rd atoms on the bottom. Remember, in this case, the particle type is just atoms, right? But it can vary. And as you can see, units of atoms cancels out, leaves us with moles, and of course 6.022 times 10 to the 23rd divided by itself is going to cancel out to be 1, gives us 1 mole. So, you can relate between the moles of a substance and the mass of a substance using the molar mass. You can relate between the moles of a substance and the number of particles using Avogadro's number. You can also use a mole-to-mole ratio to relate to the to figure out the number of moles of atoms. So, for instance, with water, right? Water is H2O. So, in one molecule of water, we have 2 hydrogen atoms and 1 oxygen. If we bring in a second molecule of water, now 2 molecules, we have 4 total hydrogen atoms and 2 oxygen atoms. If we bring in a third, we now have 6 hydrogen atoms and 3 oxygen atoms. So you can see the ratio remains the same constantly, and it's actually just the ratio from the subscript. So for every 1 molecule of water, we have 2 hydrogen atoms, 1 oxygen atom. And that ratio would keep going, and if we keep going enough, we can get all the way up to 6.022 times 10 to the 23rd water molecules, or in other words, 1 mole. So 1 mole of water would have 2 moles of hydrogen atoms and 1 mole of oxygen atoms. So that's a mole to mole ratio. So you can go to moles of atoms. And of course, from moles of atoms, if you wanted to, for that individual atom, you can figure out the mass from that type of atom using that atom's atomic mass, which is effectively its molar mass, but I'm just saying atomic mass, just to be clear that we are talking about that single atom. Of course, you could also figure out the number of that atom present using Avogadro's number.